So it says here that in a previous exercise, you guys already computed the unit tangent vector and the principal unit normal vector, right? So we already computed t and n according to this. And now the question is, well, let's compute the binormal vector and torsion. So let's see if we can talk it out. Let's see. I guess what I can do is I can do that. We can still see it. Move these out of the way. Okay. So now 42. We're looking at r of t equals, and this is three-dimensional space. They say we have 4 times the sine of t. We have 4 times the cosine of t. And then we have 10t. Now, in the answers that I just gave you guys, right, they kind of just say, well, we're going to do t cross n, and we already know t, and we already know n. I guess the question is, should I show you guys how to find those? Yeah, as a review? There's a yeah and a no. Let's do it. All right, so what is the unit tangent vector? The unit tangent vector, right? First of all, how do you get tangents? Well, you take a derivative, right? So we're going to do r prime of t. Yeah. We did this, right? So let's see. This is for cosine t, and this is negative for sine of t, and 10, right? So I know how to take derivatives. And Kim in the back is eyeing my presentation. Looks okay so far, right?
I have no idea what you're talking about, but...
But I mean, the key thing is the screen hasn't gone black.
Right.
All right. Which I figured if you're here, it won't. So
Of course not.
appreciate it. So then the magnitude of r prime, right? We can compute that. So it's the square root of this stuff squared, one at a time. So we have 16 cosine squared t plus 16 sine squared t plus 100, yeah? Right, because the cosine squared plus sine squared equals what? 1. So if we factor out that 16, add it to 100, I'm getting 116. Okay? So my t, my unit tangent vector, I guess we would have r prime of t over the magnitude of r prime of t. And so this is 1 over the square root of 116 times the vector that I started with, for sine t, for cosine t, for, oh no, just 10t. And I guess, let's see. No. Mistake made. R prime. And I wrote down R. This should be for cosine t, and this should be negative for sine t, and this should be just 10, right? Because it's R prime is what you need, not R. So we really needed this one. Okay, so now I'm guessing there's a common factor you want to take out, right? Because if you look at what the book says t is, they're going to say t of t is, well, some fraction times the vector, and I guess we're going to have 2 cosine t, negative 2 sine t, and 5, because we take a 2 out. But in order to take a 2 out, I guess we'll take a square root of 4 out of here. Right? 4 times what is 116? Well, 4 times 25 is 100. So 4 times 29. So this is 1 over the square root of 29. So there's t. Okay, there's my t. You guys with me so far?
Okay, I get it.
So that's where it's coming from. I'm taking those things out and then I'll cancel. Okay. So yeah, last time, this is our definition of n. We're going to take the derivative of that unit tangent vector with respect to, what's s mean again? Arc length. And then we normalize it to make it a unit vector. But that's kind of annoying to use, and so instead, we proved that you can do it with dt dt over dt dt, right? Over its magnitude, yeah. So I guess I'm ready now. I'm going to say, to get n of t is dt dt divided by its magnitude. Okay. So I really need dt dt. Let me compute that. So we'll kind of continue in purple over here. We have dt dt would be, well, I have this 1 over square root of 29 is a constant, so I'll leave that out front. I have negative 2 sine t. I have negative 2 cosine t. And I have a 0 now, right? Because when I take derivatives of each of these functions separately, that's what you would get. Okay, so I want to normalize it. So let's compute the length of this thing. Well, the 1 over 29, it's interesting because if you think about it, you could distribute that through, right? So let me say that when it comes to computing this, I probably want to distribute it through. And so what do I get? I get negative 2 over the square root of 29 sine of t squared plus negative 2 over the square root of 29 cosine of t squared, and then I'll take the square root of that. The other piece, of course, is just 0, so it's plus 0 squared. So this is what I'm thinking of doing. That's all right? Yeah, Paul, it's great. Oh, thanks. It's a great conversation I'm having today with you guys. So let's see, I get 4 over 29 sine squared t plus 4 over 29 cosine squared t plus 0, so I'll just do that. So I think you could see that's the square root of 4 over 29, which is 2 over the square root of 29 if I want. Right? Is this okay? So, now I'm ready to apply my formula for n. N equals something divided by 2 over the square root of 29. So n of t equals, again, some vector. Well, instead of dividing by 2 over the square root of 29, I can multiply by the square root of 29 over 2. And the nice thing about that is that the original vector had a 1 over square root of 29 in it, which all drops out, right? So these are gone. And then this 2, you'll notice cancels with, there was a negative 2 sine here, there was a negative 2 cosine here, and a 0. So I guess my normal vector worked out to be negative sine t, negative cosine t, and 0. Yeah? Okay, that's a lot of work we've done, and we haven't done any of this problem yet, right? Because
But
they,
all of that was 28.
they said, right, they said that this could have been done earlier. And did we assign 28?
You did.
Yay! All right, so we just did 28 for you. And it sounds like that was useful for some of you guys. But now what do we want to do? Now we want to compute the binormal. Okay? And the binormal is going to be the cross product of t and n. We talked about how these three vectors, guys, are going to make this beautiful frame, right? Because t and n are orthogonal. When you do the cross product, you get another orthogonal vector. It's going to look like, here, I can show it there, huh? Television audience at home sees that too. Right? So back to our program. Here we go. B equals t cross n. And so the way I'm going to do that is I'm going to take the determinant of the matrix, which I get, and here's what I'm going to do. I'm going to fill in I, j, and k. Those are my principal unit vectors, right? And then in the slots here, I'll put those coordinates that we already found. So let's see, we have, this is 2 over the square root of 29. I'll just put a c for cosine theta. Negative 2 over the square root of 29s for sine of t. And then 5. And then n, we said, was negative sine of t. I'll just put negative s. Negative cosine of t. And 0. Wow. Okay. So this is what we have to do. Any questions so far on what that means or anything like that? What I'll do is I'll write I times what? Well, times, when you take this determinant that goes with the I, you're looking at this submatrix with I, right? So that would be I times 0, because 0 times anything is 0, plus, because I have minus, but there's a minus right there, 5 cosine t. Is this okay? Next, I need a minus sign. Minus j. Now, if I look at the matrix that goes with the j, you kind of get rid of this middle term. You look here and here. And so you get 0 plus 5 sine of t. And then we get a plus vector k times what? Well, here I guess I have a little more work to do because I have, now I'm looking at this first submatrix here with the parentheses. So that would be negative 2 over the square root of 29. I'll try and write a little bigger so we can read it. Cosine squared t. And then it's funny because then you subtract, and so I have minus, minus, minus. So minus 2 over the square root of 29. And what's that give me? Sine squared t. Well, this is what I'm seeing. And so, if I did my computations right, I'm getting the following vector for b, because this thing times I, that's what goes in the first coordinate. So I'm going to get 5 cosine t, comma, and then this times j, that's what goes in the second. So I'm going to get negative 5 sine t, comma. And then here, if you factor out the negative 2 over square root of 29, you'd be left with cosine squared plus sine squared, which is 1. So I'm getting that this is our binormal vector. Is that what they have? Yeah, except
No, you back out the square root of 29.
they have a square root of 29 here and here that I don't have.
You should, you lost it from your calculation.
I did, right? Right here. Okay. So I had a 5 here. I had a negative 2 over square root of 29, and I don't know. I don't see it. I like my answer better.
No, I wasn't paying attention to that. I just did it and got what they had.
You got what they had or what
Yeah,
I had?
because your K vector and your T vector,
Yep.
when you listed it in your,
Oh, that's not a 5.
It's not 5, it's 5 over square root of 29.
That's a 5 over square root of 29. And so that changes things. That changes both of these 5s, right, from the first 2 to 5 over square root of 29. Good catch, guys. So yeah, I like the way they write it. If you have all this 1 over square root of 29 stuff going on, you may as well just factor it out. 1 over square root of 29 times 5 cosine t, negative 5 sine t, and negative 2. Yeah? Now we're happy? Now we're happy. We got part of it done. We have B done. So the other thing that they want is they want me to compute torsion. Okay? And they're going to call this tau. So let's take a look there. We're continuing. Maybe that's a reason not to use tau with the other thing I was doing with arc length. My torsion equals, and so the book says negative dB ds dot n. Okay? So I didn't have ds, but I tried to get it, but I made a mistake down here. We're not normalizing. What we're doing is we're using the chain rule. So again, using the chain rule, you could think of this as negative dB dt over ds dt. This is where Leibniz notation is really handy. So maybe dB ds is hard to compute because I don't have anything in terms of s. But I can compute dB dt and I can compute ds dt. And that's what I need to do. So I already did compute dB dt. It is up here. Now what about ds dt? Did we do that?
Well, you have to go back to the original position, right? Is that just the...
That's the arc length, right?
Right.
So if you think about arc length is an integral of, from a to t, let's say, of, and here's v prime, or I'm sorry, the magnitude of r prime of t dt. So ds dt should just be the magnitude of r prime of t, and again, these should be some other variable, u's or something, but by the fundamental theorem of calculus, it should just be the magnitude of r prime. And did we compute that already? We did, right? In the problem 28 part, we did that. Where, right up here, square root of 116. Does that look familiar? That's what I'm saying. Let me see if that works. So, if I'm right, what I get is this. 1 over the square root of 29 times negative 5 sine t, negative 5 cosine t, 0, dot n. But we have to divide by ds dt, which I'm saying is the square root of 116. Yay or nay? 29 and 116 have a common factor, we said, right? What's the common factor? 4, right? So let's see how that works. Dividing by the square root of 116 would be the same as multiplying by 1 over it. So now I'm getting, instead of dividing by square root of 116, let me multiply by 1 over the square root of 29 and the square root of 4 times this stuff I had. Yeah, this works. So if I work that out, the 29 and the 29 gives me 29, and the square root of 4 is 2. 29 times 2, 58. So really, the things I need to dot would be negative 5 over 58 sine t, negative 5 over 58 cosine t, 0, dot, now what's the normal vector? We had that. We said it was negative sine t, right? Negative cosine t, 0. And so the torsion equals, well, when I dot these two, what happens? I get positive 5 over 58 sine squared t. And when I multiply the middle coordinates, same thing, 5 over 58 cosine squared t plus 0. So I'm getting that the torsion is, if I factor out, I'm getting 5 over 58. Oh, and there's one other thing that I lost along the way, which gives us the final correct answer, and that was, see that negative sign in the formula? We lost it. Here it is, here it is, here it is, here it is, and so there's your torsion. And Kathy, you said you did it with the cross product formula instead, right? Okay. So there are definitely alternative approaches here, okay? But one nice thing I think about showing this way is this idea that I think is important in this chapter. Almost all the formulas that have derivatives, the definition is going to be something ds, an arc length parameterization. But you can still use the chain rule like this. And maybe you can't compute this derivative, but you can compute each of these. That's very common. And then the other thing to remember is, what is ds dt? ds dt, some people call it the arc length element. It's the thing you need to integrate, the speed, right? If you want to get the arc length. And so that's the magnitude of r prime of t. So maybe that helped, I don't know. Yeah, so the question asked was, how do you find tangential and normal components of acceleration? And so looking at example 7, you can kind of see what they do. They have right here an acceleration, a very simple one, 0, 2. They compute t, they compute n, and now the best thing to do is to do the projection, okay? A dot n and A dot t, okay? I think that's the best way to handle these. So let me do that with our example right here, and we'll go. So this is problem, we said something C. 61C, guys, is that what we're doing?
Yeah.
All right, let's do it. So 61, they give me two vectors. They give me R of t is t, 2t, 3t. And then another one, they say another way to write R of t would be t squared, 2t squared, and 3t squared. And so I have both of those. So again, let me show you what's going on here. We have, this is A, and this is B. And what I really have here is I have different parameterizations of the same curve. And I say curve, I should really put quotes around it, because what shape is this if you actually graphed it? Do you know? 1, 2, 3. And then if you plug in a 2 for t, you get 2, 4, 6. It's a line, right? It's a line, okay? So it's you know, in 3 space, coming up out of the origin, we're on some line. And so the question is, do you go this fast or do you go that fast? When you go t squared, it will start to speed up as you leave the origin. So it's like inverse gravity. I don't know what it is. Well, I kind of do know what it is. All right. So, but that's what we're doing here. And so, again, this was problem 61, and the question was asked about part C. And so I guess my question is, do you guys care which I do, A or B? Because my thought is I'll do one, you guys do the other. So after consulting my students, we decided I'll do part B, right? Although we said the path is basically a line in either case. So now, part B of B, yeah, so we're doing BB, right? So here we go. The velocity of t would be 2t, 4t, 6t. And the acceleration as a function of t would be the vector valued function 2, 4, 6. Beautiful. Okay, part C says, can you take that acceleration vector and write it as a scalar times the unit tangent vector plus a different scalar times the unit normal vector? And here's where I think a sketch is really instructive, so I'm going to go ahead and do it. See that little teeny sketch I did before? I'm going to make it a little bit better. Not much better, but a little better. All right, so it moves 2 in the x direction. It moves 4 in the y direction. And it moves 6 in the z direction per unit time squared. That's my acceleration. So if I can take this parallelogram and kind of reproduce it up here, then I know right where to aim with my vector. My vector is this guy. Okay. Oh, this is kind of a dumb problem now that I think about it. Well, it is. Because, first of all, what's the path? The path is right along that line, right? This is going to be boring. Because all the acceleration should be right along that line. Darn it. What a stupid problem. I'm not assigning this one again. I'll assign 63 or something. Because what I wanted to do was show you a situation where here's a curve, okay, that Let me do it this way. Suppose I'm traveling on this pretzel path, of some kind, right? So let's say I was traveling on this path. And then I have an acceleration right here. Well, what you'll do, or that wouldn't be right. Maybe the acceleration would be this vector, and that's why it's turning a little bit. But what you can do is you could say, okay, we'll divide that blue acceleration into tangential and normal components, okay? And, of course, we can compute t and we can compute n. Actually, we should do that. When you compute t, it's a unit vector moving along the same way as the velocity. When you compute n, it's a unit vector also. It is. The centripetal acceleration would be the normal component when you swing in a circular arc. Absolutely. And the tangential acceleration, right? I guess you may not even have it in your typical swinging of a circular arc in your physics class. Okay? So we'll see what happens here. Let's compute some of these things. So first of all, let's compute t. How do I get the unit vector t? Well, I'm going to take r prime, which I've been calling v, and divide by its magnitude. What's the magnitude of that thing? Do we know? 2, 4, 6, right? So I guess I have a little work to do. This is the square root of 4t squared plus 16t squared plus 36t squared, right? How am I doing so far, okay? Jesse, talk to me. Okay, so let's see, that's 20, that's 56t squared, right? So I take the square root. I could say this is 1 over t square root of 56 times 2t, 4t, 6t, although there's an absolute value here, right? Got to watch that, I guess. So I could say t is either plus or minus 1 over the square root of 56 times 2, 4, 6. So t is plus or minus. This is 14 times 4. And I can take a 2 out of here, right? And then I can cancel. This is kind of like what Jimmy was asking about before, that other simplification I did. You guys remember that? So I'm getting that the unit tangent vector is plus or minus 1 over the square root of 14 times 1, 2, 3. Wow, okay. Normal vector. So for the normal vector, I'm going to do, well, dt, d what? ds. And then we're going to normalize it. So we'll divide by dt ds. But I want to point at something out here. Guys, t is a constant, right? There's no t's anywhere in there, no little t's at all. So what's that mean this derivative is? 0 over, who cares, because this is, right? So like I said, this is kind of a dumb problem because you don't have any normal component. And actually, that should make sense to you. If you think about it, why would a particle travel in a straight line? Because or accelerate in a straight line, because all the acceleration is moving in that straight line direction, namely the direction 1, 2, 3. And that's what the thing said, whether, I don't care which parameterization you guys do, that's what it said. So this is okay. It's not very good for tangential and normal. So anyways, what's the story though? In general, how do you compute AT? Well, what the book suggests doing is let's take our vector A and dot it with T. So let's see what that does in our case. What's our vector A? Our vector is 2, 4, 6. Let's dot that with, I said, plus or minus 1 over the square root of 14, 1, 2, 3. All right, I can do that. This is plus or minus 1 over the square root of 14 of what? I guess it would be, if I dot these vectors, I get 2 plus 8 plus 18, plus or minus 1 over the square root of 14. Is that 28? So plus or minus 28 radical 14 over 14, I remember. So plus or minus 2 square root of 14 after I simplify. All that for little at. When I do an, that's going to be a dot n. But guys, what are you doing? You're doing 2, 4, 6 dot 0, 0, 0. So what do you get? You get 0. Okay. And so I guess final answer here, A of t equals plus or minus 2 radical 14 times the unit tangent vector, which is plus or minus 1 over the square root of 14, 1, 2, 3. But if you think about it now, oh, and then plus 0, right? Because we have 0 dot n is 0. So the square root of 14's cancel, the plus or minuses cancel, so we get 2 times 1, 2, 3. Isn't that the same as the original acceleration? Yeah, that's 2, 4, 6. So yeah, like I said, this is kind of a boring problem. You're better off looking at the example than you were for this problem when it comes to learning about tangential components.